Here the diagram shows in chronic Penny model how actually periodic potential it is experiencing by electron. V is equal to maximum potential V naught in the barrier. V is equal to 0 when it is in between the potential energy is 0 when it approaches any positive ion core. Positive ion. That means potential energy is 0 when it approaches positive ion. So these curves actually these curves are like this. So this chronic Penny, they modified them like square waves. That's all. They become square potential wells, rectangular square potential wells. So barrier width is B and potential well width is A. So the periodicity of the potential is A plus B. The energies and wave functions of electrons associated with this model can be calculated by solving time-independent one-dimensional Schrodinger's wave equation for the two regions 1 and 2. 1 and 2 means V is equal to 0 when it approaches a positive ion. V is equal to V naught maximum potential when it is halfway between the two ions. The Schrodinger's equations are d square psi by dx square plus 2m by h bar square into E psi is equal to 0 when x is 0 is less than x less than a. 0 is less than x less than a. That means when the particle is in between 0 and a, this value is 0. Okay. 0 and a, this is the equation. So potential energy is 0 here. That's why E psi we wrote. When x value is lying in between minus b and 0, V is equal to V is actually having some potential, which is maximum potential V naught here. So Schrodinger's time-independent wave equation becomes d square psi by dx square plus 2m by h bar square into E minus V naught, E minus potential energy, right? So potential energy is V naught. E minus V naught into psi is equal to 0 when the electron is in between minus B and 0. So let alpha square is equal to 2me by h square, 2me by h square. Then beta square is equal to 2m by h bar square into V naught minus E. Why we wrote V naught minus E, we will see. Okay, in later section. D square psi by dx square plus 2m by h bar square into V naught. Instead of here E minus V naught, we wrote V naught minus E. We are considering this as beta square. Here instead of beta square, we write minus beta square. That's all. Because beta square we assume like 2m by h bar square into V naught minus E. So 1 and 2 equations becomes d square psi by dx square plus alpha square psi is equal to 0 in the first equation when the particle is in between 0 and A, when it is in the potential well, exactly to say. Then this equation becomes d square psi by dx square plus alpha square psi is equal to 0 when 0 is less than x, 0 is less than x less than A. When this becomes the particle is in between in the potential barrier, that means that is in between two positive ions, halfway between the two positive ions, potential energy it will have. So this equation takes this form, d square psi by dx square plus what is that, beta square. Instead of beta square we write minus beta square psi is equal to 0 when it is minus b is less than x less than 0. The solution that will be appropriate for both the regions can be written in Bloch's form as psi of a solution. This is you have derived twice. That's why it is like this. The solution for these equations will be in the form of Bloch's equation. Psi of x is equal to e power ikx into uk of x. E power ikx into uk of x, where uk of x is actually uk of x plus a. uk of x, function of this particle uk of x is equal to uk of x plus a, because it will be repeated several times, no, that's why it is x plus a, because x in x direction lattice constant is actually a, that's why it is your uk of x plus a. K is actually wave vector. K is 2 pi by lambda. R propagation vector along the x direction. Okay, so it is related to momentum of the particle. So if you differentiate these equations, this equation psi of x is equal to e power ikx into uk of x. If you differentiate this equation twice, okay, with respect to x, and substituting in equation 4 and 5, equation 4 and 5, what we get? What we get after this equation, Bloch's equation, you try to derive twice, differentiate twice. After that, you substitute in above equations. Then we get this equation, because we have in the syllabus qualitative treatment only, not quantitative. Not entire thing you need to write. You can write the simplified version of this equation. I mean the final version of the equation. That is m v naught ab by h bar square into sine alpha a by alpha a plus cos alpha a is equal to cos ka. This is another equation we got. We name it as 7. Let P is equal to mv naught AB by h bar square. This one, this is P. Then this equation becomes P into sine alpha A by alpha A plus cos alpha A is equal to cos Ka. K means already I told you propagation vector or wave vector. P is known as potential barrier strength. Potential barrier strength. In the above equations, we have two variables, alpha and x. Here you see alpha and x are two variables. Okay, so the left hand side of the equation 8, the left hand side of the equation 8 is plotted as a function of alpha for p is equal to 3 pi by 2, from which the permissible values of alpha can be known. If we substitute 3 pi by 2, we can get the permissible values of alpha. Here alpha, what it represents? It represents some angle. The right hand side of the right hand side can take only values between -1 and +1, because this is cos, right? Cos varies from -1 to +1. So that is why it is written like the right hand side of the equation varies between -1 and +1. The above equation is satisfied only for the values of alpha A, for which left hand side lies between plus or minus 1. Okay, so for what values of alpha A, the left hand side will be satisfied when the values of alpha A lies between plus or minus 1. The plots are shown in this figure. See, potential barrier strength P sine alpha A by alpha A plus cos alpha A. We took on left hand side of the equation, we took on y axis. On x axis, we have taken alpha values. So what is happening here? It is periodic potential it is experiencing. So for what values of alpha you are getting, this one we are seeing alpha A. Here 0, allowed regions and disallowed regions. Allowed regions and disallowed regions it is having. So it is varying between +1 and -1. Okay, you can see -1, 0, +1. We will see now. This is 0, pi, -pi here. Okay, 2 pi, 3 pi, and it goes on. From this equation, the allowed range of alpha A satisfying equation 8 are shown by the shaded portions, which are allowed region bands. for electrons separated by forbidden regions. Okay. The allowed range of alpha A satisfying equation 8. Equation 8 in the sense just now I have shown, you know, P sin alpha A by alpha A plus cos alpha A is equal to cos A Ka. That is 8th equation. So the allowed range of alpha A satisfying equation are shown by shaded portion. Just now I told you, know, shaded regions are there. These regions are allowed regions. Okay, are allowed energy bands for electrons separated by a forbidden regions. Electrons will have allowed regions and forbidden regions also. So by plotting the curve between left hand side of the equation and right hand side, okay, then we get the values for electrons which are allowed and which are not allowed. As the value of alpha A increases, the width of the allowed energy band also increases as the width of the forbidden. I will show you the plot again. See, as the value of alpha A increases, see, width of the allowed region is getting increased. Width of the allowed region is getting increasing when alpha A value is getting increases. Okay, so as the width of the forbidden gap decreases due to the decrease of the first term in the equation. Okay, due to the first term in the equation, the allowed region, if it increases, the width of the forbidden gap decreases. Okay, very simple. If P is large, P is known as potential barrier strength. Potential barrier strength. Only alpha and x are variables in this equation. Alpha and x are variables in this equation. P is potential barrier strength. If P is large, the width of the allowed band decreases. P ఎక్కువయ్యే కొద్దీ allowed region width తగ్గిపోతుంది చూడండి. P తక్కువయ్యే కొద్దీ allowed region width ఎక్కువైపోతుంది. So if P is large, the width of the allowed band decreases and the width of the forbidden band increases. Forbidden band, okay, region is getting increased when P is large and allowed region width is decreasing. For P is infinite, P if it goes infinity, what will happen? Then equation 5 has only one solution. Equation 5 is what? D square psi by dx square minus beta square psi is equal to 0 for minus b is less than x less than 0. That is actually fifth equation. So for P is infinity, equation 5 has only one solution. What is that? Sin alpha A is equal to 0. Sin alpha A is equal to 0. Okay. Okay. That's all right. If P tends to infinity, then sin alpha can be 0. Alpha A is equal to plus or minus n pi. What values of alpha, then this sign becomes 0 plus or minus n pi. Alpha is equal to plus or minus n pi by A. Alpha square is equal to n square pi square by A square. That is equal to 2me by h square, h bar square. Okay, because alpha we considered earlier. Do you remember alpha and beta? So alpha is actually, alpha square is equal to R2me by h bar square. Then E is equal to, what you can write? Compare these two equations. E is equal to n square pi square h bar square divided by 2m into A square. Then E is equal to n square by 2m, you take out, pi square h square by 4 pi square A square. What is actually h bar? H bar is h by 2 pi. Reduced Planck's constant. H bar is equal to h by 2 pi. So h by 2 pi whole square. H square by 4 pi square. H square by 4 pi square I wrote here like this. You got now? Rest everything is same. So E is equal to the same equation. If you